Hello, my name's Hakimi, and I'm a PhD student at the Technion, Israel Institute of Technology, in the Computer Science Department. Today, I'll be presenting our work, SMEGA, Distributed Deep Learning using a single momentum buffer. This is a joint work with Cohen and Schuster. So I'll start off by explaining why do we need distributed training of neural networks. Here we can see that neural networks have a tendency to grow over the years, which results in high computational costs and long training times. To shorten the training time of these large models, the training is commonly executed by several workers, typically GPUs or TPUs, which work together to train the model. The most commonly used method for distributing the training is synchronous stochastic gradient descent, or SSGD for short. In SSGD, each worker computes its gradient on a different batch of examples. The gradients are then averaged across all workers, and the parameters are updated with the average gradient. Before computing the next gradient, the synchronization operation has to finish, during which the computational devices are idle. Consequently, the progress of SSGD is limited by the slowest worker. Here we see that even an optimized distributed neural network framework, such as Horovod, struggles to achieve true linear scalability due to the communication overhead of SSGD's synchronizations. Furthermore, we see that the communication overhead varies between different neural architectures. Asynchronous SGD, or ASGD for short, addresses the drawbacks of SSGD by limiting synchronization between the workers, allowing it to scale almost linearly. However, limiting the synchronizations induces a new problem, known as staleness. Staleness is caused by applying out-of-date gradients, and it can greatly hinder the convergence process and hurt the final accuracy. Here we see an illustration of the ASGD training process. At time t, worker I pulls the most recent parameters xt from the master. Worker I then computes a gradient git based on parameters xt. When the workers finish to compute the gradient, it pushes it to the master. However, the master's parameters have already progressed, and thus the gradient git is stale. In this example, the master progressed tau steps. The distance between parameters xt and xt plus tau is defined as the gap. When the gap is larger, then the staled gradient becomes less accurate. Here, we see a plot of the gap when training a ResNet 20 architecture on the CIFAR10 dataset. The y-axis represents the gap, and the x-axis is the epoch. We see that increasing the number of workers increases the gap, which in return reduces the gradient accuracy. This severely limits ASGD's scalability when trying to reach high final accuracy and fast convergence. Here we see a demonstration when training with staleness without parameter estimation. A worker pulls parameters theta t and computes a gradient. However, when the worker finishes to compute the gradient, the master's parameters are already tau steps ahead. This causes the gradient update to be irrelevant for these parameters. Here we see a demonstration when training with staleness with parameter estimation. A worker pulls parameters theta t and uses the momentum of all workers to estimate the future parameters of the master, noted as theta hat. The worker then computes the gradient on parameters theta hat instead of the parameters theta t. When the worker finishes to compute the gradient, it sends it to the master, which are applied on parameters theta t plus tau. We see in this illustration that parameters theta t plus tau are much closer to theta hat instead of theta t plus tau to theta t, and therefore the gradient should be much more relevant to the master's current parameters. One of the main problems of parameter estimation techniques is their high memory usage. Here we can see, for example, that the previous parameter estimation technique, known as DANA, has a high memory usage. This memory usage also increases as we add more workers, which makes it less scalable. On the other hand, we see that SMEGA is independent by the amount of workers and has a steady amount of memory usage, which is lower than DANA. One of the key ingredients in SMEGA is that it maintains a single global momentum buffer, and therefore its memory consumption is invariant to the number of workers. SMEGA works with three main steps. First, the master receives a gradient from worker I and updates the parameters according to momentum Asgd. Once the master receives n gradients, the global momentum buffer gets updated according to the accumulated gradients. Finally, the master sends an estimated future position of the parameters back to the worker. To accurately estimate the future parameters, SMEGA uses the global momentum vector with the additional knowledge of the accumulated gradients. The estimation is given by the equation below. Here we see a figure of the test error when training a RESA-20 neural architecture on the CIFAR-10 dataset. The y-axis presents the test error, so lower is better, and the x-axis is the number of workers. SMEGA achieves the lowest test error and maintains the best scalability compared to the other algorithms. SMEGA-NE is used as an ablation study and stands for without estimation. We can see that SMEGA-NE reaches a high test error relatively on low number of workers. SMEGA achieves low test error even on 64 workers. Here we see another figure of test error, but with the ResNet 50 neural architecture on the large ImageNet dataset. The y-axis is the test error, so lower is better here as well, and the x-axis is the number of workers. SMEGA outperforms all other algorithms, and once again we see that the SMEGA-NE, which is used as an ablation study, reaches a high test error. So the parameter estimation is crucial for achieving a low test error. Our code is publicly available on GitHub with support for PyTorch, given by the link below. Thank you for your time.